Break a magnet in half and you get 2 smaller magnets. Break those and you get 2 more. You can do this forever and never hold a single pole alone. But one particle, if it exists anywhere in the cosmos, would shatter that rule and rewrite every force we know. Tonight we hunt it. A signal caught one Valentine's Day and never seen again. A particle as heavy as a living cell. If mysteries like this pull you in, a like and subscribe truly help. Prepare yourselves. We begin. Take a bar magnet off your refrigerator and snap it cleanly in 2. You might expect to end up with a loose North Pole in one hand and a loose South Pole in the other. That is what feels natural. Every magnet has a north end and a south end, so cutting it right down the middle should separate them. Try it, and something strange happens instead. Each broken half instantly grows a brand new pole. The piece that held the north end sprouts a fresh south. The piece that held the south end sprouts a fresh north. You are holding 2 complete magnets, each with both poles, each smaller than before. So you cut again, and again. You could keep going down to a sliver you can barely see. The result never changes. 2 poles, always paired, always together. Even if you could slice the magnet down to a single atom, that atom would still behave like a tiny magnet with a north side and a south side. The pairing follows you all the way to the bottom. Picture a long line of tiny arrows, all pointing the same way, packed shoulder to shoulder inside the metal. The head of each arrow is a north pole. The tail is a south pole. When you snap the magnet, you slice between 2 arrows, and suddenly a fresh head and a fresh tail are exposed at the new edges. There is no place you can cut where a head sits alone with no tail behind it. The arrows go all the way through. This is the deepest habit in all of magnetism. A north pole and a south pole come as a set, welded together, impossible to pull apart. Physicists have a name for a magnet with 2 poles. They call it a dipole. The word simply means 2 poles. Every compass needle, every horseshoe magnet, every magnetic strip on a credit card, every magnetic field wrapped around the Earth itself is a dipole. 2 poles, bound for life. And it runs deeper than bar magnets. The magnetism inside iron comes from electrons, the tiny charged specks whirling inside every atom. Each spinning electron is itself a minuscule magnet, with its own north and its own south. Stack enough of them pointing the same direction, and their little fields add up into the pull that lift a paperclip. Even at that smallest level, the level of a single electron, the 2 poles refuse to separate, so the rule feels absolute. It feels like a law carved into the universe. Wherever there is a north, there is a south close behind. You cannot buy a lone pole, you cannot build one, you cannot cut one free. In every experiment ever run, in every corner of nature ever examined, magnetism arrives 2 poles at a time, which makes the whole thing sound settled. Case closed. A magnet has 2 ends, and that is simply how reality works. Except reality has a matching partner to magnetism, a force so similar that the 2 are woven together in every equation physicists write. And in that partner force, the rule is broken constantly, casually, everywhere you look. Lone charges are ordinary there. They sit in every wire and every spark. So why does one force allow loners while its twin forbids them? That question is where the trouble begins. Sprinkle iron filings on a sheet of paper and hold a magnet underneath. The specks leap into a pattern, curved lines sweeping out from one end of the magnet and arcing back into the other. Those lines trace the magnetic field, the invisible region of push and pull that surrounds every magnet. Look closely and you notice something worth pausing on. Every single line is a loop. It leaves the North Pole, curves through the air and returns to the South Pole. Then it continues straight through the inside of the magnet back to where it started. No line ever stops in mid-air. No line ever begins from nothing. They all close on themselves like loops of string. Now do the same for electricity, and the picture changes completely. Take a single speck of electric charge, say a lone electron. Its electric field lines shoot straight outward in every direction, like spikes on a sea urchin, racing away to infinity. They start at the electron and they simply leave. They have a definite beginning. That beginning is the charge itself. Here is the difference laid bare. Electric field lines can start at a point and end at a point, because electric charges exist as separate sources. A positive charge is where the lines begin. A negative charge is where they end. Magnetic field lines have no such starting point. They can only loop. Physicists capture this with one short, elegant statement. The magnetic field has no source. Wherever field lines go out, exactly the same number must come back in. Add it all up around any closed surface, any bubble you draw in space, and the magnetism passing outward perfectly cancels the magnetism passing inward. The total is always zero. Draw the same bubble around an electron and the total does not cancel. Charge leaks out. The books do not balance, and that imbalance is the electron announcing its presence. Think of it like water. An electric charge is a faucet, a place where water gushes into the room. A magnetic field is a river current with no faucet at all, water flowing in great circles, always returning, never pouring in from a hidden tap. Search the whole river, and you find no source. The water was always going in a loop. This is how scientists know, with brutal confidence, that isolated magnetic poles have never shown up. If a lone North Pole existed, it would be a magnetic faucet. Field lines would burst out of it and race away, exactly the way electric lines burst from a charge. Someone, somewhere, in a century of careful measurement, would have caught a bundle of magnetic lines with a loose end. No one ever has. Every magnetic map ever drawn shows loops and only loops. So the rule is written into the mathematics itself, into the equations that describe every motor, every generator, every radio wave crossing the room right now. Magnetism loops, electricity leaks. One force has lonely sources, the other has none. And that lopsided arrangement bothered physicists for a very long time. The two forces are otherwise so alike, so tightly braided, that the missing piece felt less like a law and more like an absence. Something that ought to be there, gone quiet. A gap that big usually means a discovery is waiting inside it. Spin a magnet inside a coil of copper wire, and electricity flows through it. That single fact runs the world. Every power plant on Earth, whether it burns coal or splits atoms or catches the wind, does the same basic thing. It spins magnets near wires to push electric current into the grid. Move a magnet, make electricity. And the reverse works too. Run electricity through a wire, and a magnetic field wraps around it. Feed current into a coil, and it becomes a magnet you can switch on and off. This is how electric motors spin, how speakers make sound, how a scrapyard crane lifts a car. Sit with that for a moment. Electricity makes magnetism. Magnetism makes electricity. Push on one and the other answers. They behave as two faces of a single deeper force, and physicists gave that force one name: electromagnetism. The person who stitched them together was James Clerk Maxwell, a Scottish physicist working in the 1860s. He wrote down a small set of equations that treated electricity and magnetism as one unified thing. Those equations did something no one expected. They predicted that a wiggling electric and magnetic field could break free and travel through empty space as a wave, moving at one fixed speed. When Maxwell calculated that speed, it matched the measured speed of light exactly. Light itself turned out to be an electromagnetic wave, a ripple of these two braided fields racing across the universe. The glow of every star, the warmth of the sun on your face, the signal reaching your phone, all of it is electricity and magnetism dancing together. Later, Albert Einstein pushed the unity even further. He showed that whether you see an electric field or a magnetic field can depend simply on how fast you are moving. Stand still beside a charge, and you measure a pure electric field. Run past that same charge and part of it now looks magnetic to you. The two are so deeply the same that motion alone can turn one into the other. They are like the front and back of a single coin, and which side you see depends on your point of view. So the two forces are as close as two things can possibly be. They share equations, they share a wave, they melt into each other under motion. In almost every way, whatever is true for one is mirrored in the other, which makes one difference scream out. Electricity has isolated charges, lone electrons, lone protons, positive here, negative there, sitting alone in every atom and every bolt of lightning. Magnetism, the mirror twin, the other face of the very same coin, offers no such loners. The magnetic version of the electron is simply missing. The symmetry is broken at exactly one spot, and it is a glaring spot. If these two forces truly are reflections of each other, The reflection should be complete. Every electric loner should have a magnetic partner staring back. Yet on the magnetic side of the mirror, that partner is absent. The glass is empty where a face should be. Physicists could have shrugged and called it a quirk of nature. Some did. But one man refused to look away from that empty patch of mirror. He asked what the universe would look like if the missing face were real. His answer would tie the smallest rule of electricity to the existence of a single, undiscovered particle. Somewhere in a physics textbook sits an equation with a zero in it, and that zero is the whole mystery in a single symbol. Maxwell's description of electromagnetism boils down to 4 short statements. Together they explain every electric and magnetic thing that has ever happened. They are among the most tested, most trusted equations in all of science. Whole industries of technology stand on them, and 2 of those 4 statements are near mirror images of each other, one for electricity, one for magnetism. The electric one says this in plain terms. Electric field lines can start and stop at charges. Wherever you find a lone charge, field lines pour out of it or dive into it. The equation includes a term for the amount of electric charge sitting at any spot. Put charge there, and the field responds. The magnetic statement looks almost identical, with one crucial change. Where the electric version has a term for charge, the magnetic version has a zero. Flat, blunt, deliberate. It says the amount of magnetic charge at any spot is always none. Everywhere, forever, exactly zero. That is the equation announcing, in the strictest language physics has, that lone magnetic poles do not exist. Think of the 4 equations as a beautifully balanced machine with matching parts on the left and right. Almost every gear on the electric side has a twin on the magnetic side, except for one gear. On the electric side there is a slot for charge. On the magnetic side, that slot is welded shut with a zero. The machine is symmetric everywhere but that single point. For a long time, that zero seemed like plain honesty. Scientists put it there because no one had ever measured a magnetic charge, so the equation reflected the world as observed. 0 poles found, 0 poles written. Simple bookkeeping. But look at the machine again with fresh eyes, and the zero starts to feel less like honesty and more like a wound. If you deleted it and wrote in a term for magnetic charge, matching the electric side exactly, the 4 equations would snap into perfect symmetry. Every electric rule would gain its magnetic twin. The equations describing generators and light and radio would become flawlessly balanced, elegant in a way today's version never reaches. The only cost would be admitting one new thing into the universe, a magnetic charge. A lone pole? Physicists find that kind of thing almost unbearable. When a theory is nearly symmetric and only one small piece breaks the pattern, the missing piece tends to nag at them for decades. Nature usually loves symmetry. A broken symmetry is a puzzle begging for a reason. Either the universe has a genuine gap, or it hides something we have failed to catch. So the zero became a challenge rather than an answer. Erase it, and the equations grow more beautiful. Keep it, and you accept that electricity and magnetism, twins in almost every respect, differ at one strange and lonely point. The equations themselves stay silent on which choice is correct. They work perfectly with the zero. They would also work perfectly with a magnetic charge written in. Mathematics allows both worlds. Only experiment can decide which one we live in. And that blank slot, that welded gear, that suspicious zero, was exactly what a young and unknown physicist stared at one day in 1931, wondering what it would cost the universe to fill it in. Imagine a universe where every electric charge suddenly became a magnetic pole, and every magnetic pole became an electric charge. You swap them completely. Every electron turns into a lone north pole. Every magnet turns into a bundle of electric charge. Then you ask a simple question. Would the laws of physics still work? If magnetic poles existed, the astonishing answer is yes. With lone poles added to the universe, the equations of electricity and magnetism become so perfectly balanced that you could trade the 2 forces for each other and nothing would break. Every rule about electric charges would turn into an identical rule about magnetic poles. The whole structure would keep humming along, unbothered, as if you had simply relabeled the parts. Physicists call this hidden balance duality, a deep symmetry where 2 things that look different are secretly the same law, wearing two costumes. We do not live in that fully balanced universe, as far as anyone has measured, but the equations quietly reveal that we almost could. The only ingredient missing to unlock this beautiful swap symmetry is the lone magnetic pole. Add one kind of particle, and a whole new symmetry of nature clicks into place, a mirror that reflects electricity into magnetism and back again. Symmetries like this are the most precious things in physics. Again and again, when scientists found a hidden symmetry in their equations, it turned out to reveal something true and deep about reality. Symmetry between different directions in space gave us the law that momentum is conserved. Symmetry in the flow of time gave us the conservation of energy. Over and over, a balance in the math pointed to a rule the universe actually obeys. So when the equations of electromagnetism whisper that a grand swap symmetry is sitting right there, one particle away from being real, physicists lean in hard. Here is the tantalizing part. In this dual picture, electricity and magnetism become equal partners, and the strength of one is tied to the strength of the other in a precise way. The feebleness of one force would be balanced by the ferocity of its twin. That relationship is a sharp mathematical link, precise enough to pin down numbers, and it hints that a magnetic pole, if it exists, would carry a very particular and very large amount of magnetic charge, set by the size of the ordinary electric charge we already know. Modern physicists have taken duality and run with it far beyond simple magnets. In the deepest theories of matter, versions of this electric and magnetic swap show up again and again, helping scientists solve problems that would otherwise be hopeless. A brutally hard question about strongly interacting particles can sometimes be flipped through a duality into an easy question about their magnetic mirror images. The idea born from a missing pole in Maxwell's equations grew into one of the most powerful tools in all of theoretical physics, and it all rests on a single ingredient that has never been seen. The lone magnetic pole is the key that would unlock the full symmetry, the missing partner that would let the mirror stand complete. So the pressure was building, the equations wanted the pole, the symmetry wanted the pole, the mathematics kept pointing at an empty chair at the table, insisting someone should be sitting there. In 1931, a quiet, strange, brilliant young man finally pulled that chair out and asked what would happen if he let just one pole exist. His answer stunned everyone, because it reached out and explained something no one thought was connected to magnets at all. Paul Dirac barely spoke, and when he did, every word landed like a dropped stone. Among the physicists of his time, he was famous for his silence. Colleagues joked that a unit of the fewest words per hour should be named after him. He disliked small talk, avoided crowds, and answered questions with a single sentence when one would do. Yet inside that quiet mind lived some of the boldest mathematics of the 20th century. Dirac trusted equations the way other people trust their own eyes. If the math said something strange was true, he believed the math, even when the strangeness seemed impossible. A few years before 1931, Dirac had already stunned the world. He wrote an equation describing the electron that accidentally predicted a mirror version of it, a particle with the same mass but opposite charge. People doubted him. Then experimenters found exactly that particle, the anti-electron drifting in through cosmic rays. Dirac had pulled a whole new kind of matter out of pure mathematics before anyone saw it. That success gave him a certain fearlessness. When his equations pointed somewhere bizarre, he was willing to follow, so he turned to a puzzle that had bothered physicists quietly for years. Every electric charge in the universe comes in exact multiples of one basic amount, the charge of a single electron. You never find a particle carrying 1.5 electron charges, or a third of one wandering freely, or any odd fraction. Charge comes in clean, identical packets, like eggs, sold only by the dozen. This is called charge quantization, and it is one of the most precise facts in nature. Every proton carries a charge exactly equal and opposite to every electron, matched to more decimal places than almost anything else physicists measure. The strange thing was that nobody could explain why. The equations of electricity did not demand it. As far as the basic laws were concerned, a particle could have carried any random amount of charge at all. Yet reality insisted on perfect, identical packets. Something was forcing the universe to be tidy, and no one knew what. Dirac attacked the problem from a completely unexpected direction. Instead of studying electric charges, he imagined a single magnetic pole, the very thing everyone said did not exist. He placed one lone north pole in his equations purely as a thought experiment to see what quantum mechanics would require if even one pole existed somewhere. This is the kind of move that made Dirac Dirac. Faced with a mystery about electricity, he reached for a magnet that had never been found and asked the math to tell him a story. Most physicists would have called that a waste of time. Dirac called it Tuesday. He worked through the quantum behavior of an electron circling a lone magnetic pole. The mathematics grew delicate and beautiful, full of the wave-like nature that governs the tiny world. And as the equations resolved, they spat out a condition, a rule that had to hold for the whole picture to make sense. A relationship between the electron's electric charge and the pole's magnetic charge. When Dirac read what that relationship meant, he must have felt the floor tilt. The rule connecting the two charges did something no one expected. It reached across from the undiscovered magnet and grabbed hold of every electric charge in existence. What it demanded of them would change how physicists saw the universe. Dirac's equation delivered a verdict that sounded almost too grand to believe. If a single magnetic pole exists anywhere in the entire universe, then every electric charge everywhere must come in exact, identical packets. One lonely magnet sitting in some distant corner of space would reach across the cosmos and force every electron, every proton, every speck of charge to obey the tidy rule that had puzzled everyone. The mystery of why charge comes in clean multiples would be solved in a single stroke. Take a moment with how bizarre that connection is. Charge quantization is a fact about electricity, about the particles in your own body. The magnetic pole is a thing no one has ever seen, possibly lurking billions of light years away. Dirac's mathematics tied them together with an unbreakable thread. The existence of the far-off pole and the tidiness of your electrons became two sides of one rule. You cannot have the pole without the tidy charges, and the tidy charges are exactly what we observe. The logic behind it comes from the strange rules of the quantum world. Down at the smallest scale, particles behave like waves, and those waves have a kind of phase, like the position of a hand sweeping around a clock face. When an electron travels through the magnetic field of a lone pole, its quantum wave gets twisted as it goes. For the whole description to stay consistent, for the electron's wave to line up with itself properly after circling the pole, the twist has to come out just right. It has to complete a whole number of turns, and that whole number demand is exactly what forces the electric charge into clean, identical packets. Picture winding a clock. If you turn the hand, you can stop it anywhere on the dial, but imagine a special clock where the hand is only allowed to land exactly on the 12, never between the numbers. Something in the mechanism forbids the in-between positions. The lone magnetic pole acts like that hidden mechanism for electric charge. It permits only the clean, whole values and forbids every messy fraction. With the pole in the picture, charge simply cannot be anything but tidy. This was a staggering thing to pull out of a thought experiment. Dirac had gone looking for the reason electric charge comes in packets, and the answer that fell out was a magnet no one had ever found. The two greatest puzzles, why charge is quantized and whether monopoles exist, turned out to be locked together. Solve one and you solve the other. And the argument runs in a direction that is hard to shake off. We already know charge is quantized. We measure it constantly with breathtaking precision. So the tidy packets are real beyond doubt. Dirac showed that a single pole would guarantee those tidy packets. The pole would neatly explain something we know is true, using nothing but the laws of quantum mechanics. That is why so many physicists came to believe monopoles must be out there somewhere. The universe already shows us the fingerprint the pole would leave, the perfect quantization of charge. It is as if we found footprints in fresh snow leading to a locked room, strong evidence that someone walked there, even though we have never met the walker. But Dirac's argument only said a pole could exist and would explain the tidiness. It stopped short of saying the pole must exist, or where to find it, or how heavy it would be. For those answers, physics would have to wait 40 years, until a deeper theory turned monopoles from a possibility into a promise. If the proton's charge were off from the electrons by the tiniest sliver, you would not be here to wonder about it. Every atom is a careful balance. In the centre sits the nucleus, packed with positively charged protons. Around it swarm negatively charged electrons, one electron for each proton. The positive and negative charges match exactly. so the whole atom comes out neutral, electrically silent to the outside world. That neutrality is why matter can clump together into molecules, cells, rocks, and people. Neutral atoms sit peacefully side by side. Now imagine the proton's charge were just a hair larger than the electrons, off by even a minuscule fraction. Then every atom would carry a faint leftover charge, all of them the same sign, and charges of the same sign push each other apart hard. Multiply that tiny push across the countless atoms in a human body or a planet, and the force becomes monstrous. Everyday objects would blast themselves to pieces from the inside. Your own hand holds so many atoms that even a whisper of leftover charge on each one would tear it apart with a force stronger than gravity crushing a star. So the fact that protons and electrons carry precisely opposite charges, matched to an almost unbelievable number of decimal places, is one of the quiet miracles holding the world together. Physicists have measured how equal these charges are, and the balance holds to a level that boggles the mind, far finer than 1 part in a billion billion. The universe walks a razor's edge, and matter survives only because it stays perfectly balanced on that edge. Here is the deep discomfort. A proton and an electron are wildly different objects. A proton is a bulky bundle built from smaller particles called quarks, glued together by the strong force. An electron is a tiny, simple speck with no known inner parts at all. They share almost nothing in their makeup, yet their charges match to staggering precision, opposite and equal, as if they had agreed on a number in advance. Why should two such different things carry charges locked together so perfectly? Ordinary electromagnetism offers no reason. The equations are perfectly happy to let a proton and an electron carry slightly mismatched charges. Nothing in the basic laws forces the balance, and yet the balance is there, holding the universe together with inhuman precision, waiting for an explanation. This is where Dirac's lonely magnet reaches back into the story. If a single monopole exists, then charge must come in exact multiples of one fixed unit. The proton would carry precisely 1 unit. The electron would carry precisely 1 unit of the opposite sign. The pole forces every charge in the universe onto the same rigid grid, so two utterly different particles land on the same value by a rule stamped across all of reality. That is a far more satisfying answer than blind luck. Without the pole, the perfect charge balance is a cosmic coincidence hanging by a thread. With the pole, it becomes an ironclad law. One picture leaves a fragile accident, the other delivers a certainty. So the stakes of finding a monopole climb higher. It would tell us why atoms stay neutral, why matter holds together, why you do not detonate where you sit. The tidiness of charge is the reason the universe can build anything at all. And the theory that promised to deliver these poles came with a second shock. It said the poles would be born as some of the heaviest single particles the universe has ever made. Dirac's magnetic pole came with a ghostly attachment, a thread of pure mathematics that nobody could ever see. When Dirac worked out how to fit a lone magnetic pole into his equations, a curious problem appeared. Remember that magnetic field lines normally form closed loops, always returning to where they began. A true lone pole breaks that habit. Its field lines burst outward in every direction and race away, exactly the way electric lines leave a charge. To make the mathematics describe those outward bursting lines, Dirac found he needed something to feed the field into the pole from behind, like a hidden supply line. So he imagined an infinitely thin string trailing away from the pole, carrying magnetic field into it from far away. Down that string, all bunched together, ran the field lines that then spread out from the pole in every direction. The string was a bookkeeping trick, a way to satisfy the equations, and it had one very strict requirement. The string had to be completely invisible. No experiment could ever be allowed to detect it, or the whole picture would fall apart. A pole with a visible string attached would be a fake, a dressed-up ordinary magnet. Making that string undetectable is where the magic happened. Dirac showed that the string can be hidden perfectly, but only if the electric charge and the magnetic charge obey a precise relationship. Get that relationship right, and the string vanishes from every possible measurement, leaving behind a clean, genuine lone pole. Get it wrong, and the string becomes real and visible, spoiling everything. The demand that the string stay invisible is exactly the demand that forces electric charge into tidy, quantized packets. Picture a magician threading a needle behind a curtain. the audience sees only the finished trick, a rabbit appearing from nowhere. The thread that made it work is real, but arranged so carefully that no one in the seats can ever catch it. Dirac's string is that hidden thread. It has to exist for the equations to work, and it has to be impossible to see for the pole to count as real. The universe permits the trick only when the numbers line up perfectly. For decades, physicists argued about whether this ghostly string meant the whole idea was a mathematical illusion. Maybe the string was a sign that lone poles could not truly exist, that Dirac had built a paper monster. The debate ran on and on. Some brilliant minds insisted the string was a fatal flaw. Others insisted it was harmless bookkeeping, a coordinate trick with no physical meaning, like the seams on a globe that mark nothing real about the Earth. The argument was finally settled in a beautiful way. Physicists learned to describe the pole without any string at all, using a more sophisticated mathematical language that wraps around the pole smoothly, the way many small maps can cover a globe with no seam left over. In that cleaner description, the string disappears entirely, and the lone pole stands on its own, perfectly consistent. The charge quantization rule survives stronger than ever. The ghost thread was only ever an artifact of clumsy mathematics, so the lone pole passed its hardest early test. It was strange, it was demanding, it dragged an invisible thread behind it, and still it held together as a genuine possibility. The equations blessed it. The quantum rules blessed it. Charge quantization gave it a reason to be real. All that remained was to find one, and to find one, physicists first needed to know what a monopole would actually be made of, and where such a thing could possibly come from. Electromagnetism, the force that runs your whole life, is secretly rather weak. That sounds wrong. Electricity powers cities and lightning splits trees. But at the level of single particles, the electric force has a surprisingly gentle grip. Physicists measure that grip with a famous number, close to 1/137. It sets how strongly a single electron feels the pull of electric and magnetic fields, and it is small. Compared to what it could be, the electric charge of an electron is a soft handshake, a modest tug. This gentleness is why atoms are mostly empty space, why chemistry is delicate, why light passes through glass instead of shattering it. Now recall Dirac's rule, the tight relationship linking electric charge to magnetic charge. That relationship works like a seesaw. The two charges sit on opposite ends, and their product is fixed. Push one down and the other rises. Since the electric charge is small, its partner on the other end of the seesaw must be large. The magnetic charge of a lone pole would be enormous, roughly 70 times bigger than the electric charge of a proton, measured in the natural way physicists compare them. Sit with that word, enormous. The magnetic pull of a single lone pole would dwarf the electric pull of a single proton. Where electricity gives a soft handshake, a magnetic pole would deliver a crushing grip. The very weakness of everyday electricity guarantees through Dirac's seesaw that its magnetic twin would be ferocious. This flips our whole intuition about magnets. The magnets on your fridge are weak precisely because their two poles nearly cancel, north pulling one way while south pulls the other, their effects almost undoing each other at any distance. A lone pole has nothing to cancel it. All of its magnetic power points one way, undiluted, unopposed. It would be the most concentrated source of magnetism the universe knows how to make, packed into a single point. Think of ordinary magnetism as two people playing tug-of-war on a rope, straining hard but going nowhere because they pull against each other. That standoff is why a normal magnet, for all its internal effort, produces only a modest field. A lone pole is one of those people with the rope suddenly cut, all that strength flying free in one direction with nothing to resist it. The hidden ferocity was always there, buried in the balance. Remove the balance and it erupts, and the magnetic charge would come in fixed units, just as electric charge does. You could have a pole with 1 unit, or 2 units, or 3, but never a fraction in between. The same tidiness that Dirac's rule stamps on electric charge stamps itself on magnetic charge as well. Poles, if they exist, would be as neatly quantized as the charges in your atoms, each one carrying a whole number of these large magnetic units, so the portrait sharpens. A monopole would be a single point in space with a magnetic grip dozens of times stronger than a proton's electric one, quantized into clean units, utterly unlike any magnet ever handled. Nothing in ordinary experience prepares you for an object like this, which raises an unsettling question. If such a fierce little thing came flying through ordinary matter, through the air, through your body, through solid rock, what would happen to everything in its path? The answer is violent enough that scientists built their detectors around it. A single magnetic pole flying through your body would leave a trail of destruction thousands of atoms wide. We saw that a lone pole carries a magnetic grip dozens of times stronger than a proton's electric one. Now follow what happens when that fierce little object moves. A magnet in motion drags its powerful field along with it, and that field yanks hard on every charged particle it passes. Atoms are full of charged particles, electrons whirling around nuclei. As the pole streaks by, its violent field rips electrons clean off their atoms, one after another, in a long continuous line. Physicists measured how brutal this would be. A lone pole tearing through matter would strip away electrons roughly 4,700 times more fiercely than a fast-moving proton doing the same journey. A proton punching through a material leaves a faint, thin trail of damage. A monopole would carve a wide, blazing scar, a corridor of torn atoms far brighter and far more destructive than almost anything else that could pass through. This ferocity is a gift to scientists, because it means a monopole cannot travel quietly. Anything that rips through matter, that violently announces itself loudly, it leaves an unmistakable signature, a trail so intense that no ordinary particle could fake it. If you build a detector that watches for extreme trails of torn atoms, a passing pole would light it up like a flare in the dark. Picture the difference between a needle and a chainsaw drawn across a sheet of paper. A proton is the needle, leaving a thin scratch you have to squint to see. A monopole is the chainsaw, gouging a wide, ragged gash impossible to miss. That gash is exactly what monopole hunters look for. They do not need to catch the pole itself. They only need to find the enormous wound it leaves behind. The trail also tells scientists something about magnetic charge directly. The strength of the damage depends on how many units of magnetic charge the pole carries. A pole with 2 units would tear even more violently than a pole with 1, so the width and intensity of the scar would reveal not only that a pole passed, but how much magnetic charge it held, letting physicists read the pole's identity from the ruin it leaves. There is a strange beauty in this. The very property that makes a monopole so exotic, its fierce concentrated magnetism, is also what would make it impossible to hide. A weak particle can slip through the world unseen. A monopole is too loud, too violent, too magnetically fierce to pass without a trace. It carries its own alarm. This is why so many monopole experiments are built from materials that record the passage of heavily damaging particles. Some use special plastics that develop tiny etched pits wherever an intense trail rips through, pits that can be revealed later with chemicals and studied under a microscope. A monopole crossing such a sheet would leave a line of unusually large pits, a fingerprint no common particle could match. The plastic simply waits, sometimes for years, ready to catch a single crossing. So we know how a monopole would betray itself. We know it would carry a huge quantized magnetic charge. We know it would slice through matter like nothing else. What we still do not know is where such a thing could come from, and why anyone believes the universe ever made one. For that, physics needed a theory far grander than Dirac's, a theory that tried to fuse the forces of nature into one. For 40 years after Dirac, the monopole was only a maybe. Dirac had shown that a lone pole could exist and would explain the tidiness of electric charge. But could was the strongest word available. His argument allowed monopoles into the universe without insisting on them. A person could accept all of Dirac's mathematics and still shrug and say the universe simply chose to skip them. The pole remained optional, a guest who might or might not arrive. Then, in 1974, 2 physicists working separately changed everything. Gerard 't Hooft in the Netherlands and Alexander Polyakov in the Soviet Union, unaware of each other's work, reached the same startling conclusion at nearly the same moment. In certain deep theories about how the forces of nature fit together, monopoles become mandatory. If those theories are correct, the universe has no choice. Poles must exist. This was a colossal shift. Dirac offered a permission slip. These two men delivered a command. Their results said that whenever nature unifies its forces in a particular grand way, magnetic poles pop out automatically as a consequence, woven into the very structure of the theory. You cannot have the unified forces without also getting the poles. They come as a package. The reason lies in the shape of the fields that fill space. In these grand theories, space is filled with a special field, a bit like the field that gives particles their mass. That field can point in different directions in an abstract mathematical sense, the way a weather vane can point north or east or west. Across most of space, the field settles into a smooth, calm pattern. But in certain spots, the field gets twisted into a knot that cannot be combed out no matter how hard you try. That trapped knot, that snarl in the field that refuses to unwind, is a magnetic monopole. Picture trying to comb the hair on a fuzzy ball so that it lies perfectly flat everywhere. No matter how you comb, you always end up with at least one cowlick, one point where the hair sticks up and will not lie down. Mathematicians proved this long ago. Some patterns simply cannot be smoothed away. The monopole is nature's cowlick, a spot where the field cannot lie flat, forced into existence by the geometry of the theory itself. This gave monopoles a completely new kind of reality. They had become more than a clever idea bolted onto physics by hand. They emerged on their own, unbidden, from the mathematics of unification. If you believed the forces of nature were once joined together, and many physicists had powerful reasons to believe exactly that, then you were nearly forced to believe in poles as well. The two ideas were bound together, and that raised the stakes enormously. Grand unification was one of the most beautiful ideas in physics, the dream of showing that the different forces are really one force wearing different masks. If that dream was true, monopoles were real, out there somewhere, a direct and testable consequence of the deepest symmetry in nature. Finding one would be powerful evidence that the forces truly were once united. Finding none, after searching hard enough, would put pressure on the whole grand vision. So the monopole became a messenger. Catch it, and it would carry news from an era when all the forces of nature spoke with a single voice. But this new kind of monopole, born as a knot in a unified field, came with a price tag that staggered everyone who calculated it. To tie that knot, the universe would have to pour in an almost unimaginable amount of energy. Most particles are fragile things, flickering into existence and falling apart in a fraction of a heartbeat. The heavy particles made in colliders often survive for less than a trillionth of a second before they crumble into lighter pieces. Decay is the normal fate. Almost everything nature builds at high energy comes undone almost instantly. But the monopole born as a knot in a unified field is different in a way that reaches down to its very foundation. It cannot fall apart. It is, as far as physics can tell, completely immortal. The reason is the knot itself. Recall that a monopole is a twist in a field that cannot be combed smooth, a cowlick that refuses to lie flat. The knot is locked by the shape of the field, by a kind of counting rule that mathematicians call topology, rather than by any delicate balance that could slip. The knot represents a whole number, a 1, and there is no smooth path from 1 to 0. To untie the knot, the field would have to pass through shapes it simply cannot reach without tearing space itself, so the knot stays forever. Think of a rubber band looped once around a pole. You can slide it up and down, stretch it, twist it, but you can never get it off without cutting it or lifting it over the end. As long as the loop is there, it stays there. The monopole is like that loop. Wound once around a mathematical pole, it can never escape. Its stability comes from geometry, the most unbreakable kind of stability there is. This immortality has a staggering consequence. If the universe ever made monopoles, even long ago in its first violent moments, those monopoles would still be here. They could not have decayed away. They could not have quietly vanished. Every single pole ever created in the history of the cosmos should still be drifting through space right now, as real and as heavy as the day it formed. Time cannot destroy them. Only meeting an opposite pole, a knot wound the other way, could unwind one, and in the vast emptiness of space, such meetings would be rare. So monopoles, if they exist, are relics. They're among the few things that could carry an unbroken memory of the universe's birth, survivors from an age when the forces were one, still wandering the dark billions of years later. Finding one would be like finding a coin minted in the first second of time, untouched, unworn, exactly as it was made. This is why the immortality matters so much for the hunt. Scientists do not need the universe to be making fresh poles today. It almost certainly is not, since no natural process now has enough energy. They only need the universe to have made some once, long ago. Those ancient poles would still be out there, patient and indestructible, waiting to be caught. And here the story takes a troubling turn, because if monopoles are immortal, and if the early universe made them in the way the grand theories predict, then a simple calculation follows. Scientists can estimate how many the young cosmos would have stamped out, and knowing none could ever decay, they can add them all up to see how many should fill the universe today. When they ran that calculation, the answer came back so wrong, so wildly impossible, that it threatened to break cosmology itself. The universe, by that reasoning, should be drowning in monopoles. Turn up the heat high enough and the different forces of nature begin to blur into one another. Today, nature runs on several distinct forces. There is electromagnetism, the force of light and electricity. There is the strong force, which glues the cores of atoms together. There is the weak force, which drives certain kinds of radioactive decay. These three feel completely different in everyday life. One lights your home, one holds matter together, one makes some atoms crumble. They have different strengths and different reach. They seem like separate tools in nature's kit. But physicists discovered something remarkable when they studied how these forces behave at higher and higher energies. Their strengths change. The strong force gets weaker as energy climbs. The others shift too. And when scientists extended the trends upward toward almost unthinkable energies, the three forces appeared to converge, their strengths sliding toward a single common value. At a high enough energy, they would meet. They would become, in a sense, one unified force, indistinguishable, ruled by a single grander symmetry. This is the dream of grand unification. It says that in the searing heat of the very early universe, when everything was hotter than anything that exists today, the three forces were merged into one. There was a single unified force governing everything, elegant and whole. Then, as the universe expanded and cooled, that unity shattered. The one force split into the three we know, the way steam cools into water and then freezes into ice, each stage looking utterly different from the last. That shattering has a name. Physicists call it symmetry breaking. When the unified force broke apart, the perfect symmetry of the early universe was lost, frozen into the messier arrangement of separate forces we see now. And symmetry breaking, it turns out, is exactly the kind of event that leaves knots behind. Here is the beautiful connection. When the unified field cooled and settled, it had to pick directions, the way cooling water molecules pick how to line up as they freeze into ice. Different regions of the young universe, far apart and out of touch, picked their directions independently. Where those mismatched regions met, the field could not line up smoothly. It got caught in a twist, a knot that could not be combed away. Each of those trapped knots was a magnetic monopole. So monopoles are the scars of a broken unity. They are the flaws left in the cosmic ice as the universe froze from one force into many. Picture a vast lake freezing overnight. A lake freezes in patches that grow and collide, and where the patches meet at odd angles, cracks and flaws appear. The universe froze the same way, and its flaws were poles, permanent creases where the cooling forces failed to agree. This gave monopoles a majestic origin. They would be direct relics of the moment the forces divided, physical evidence that all of nature's forces were once a single thing. To hold a monopole would be to hold a fragment of that lost unity, a scar from the instant the universe chose to become complicated, and the energy of that instant, the heat at which the forces unified, sets how heavy each monopole would have to be. When physicists worked out that mass, they arrived at a number so large for a single particle that it barely seems to belong in the world of particles at all. One pole would weigh as much as a living thing you could see under a microscope. One magnetic monopole would weigh about as much as a bacterium, and that sentence should stop you cold. Every particle you have ever heard of is almost weightless by human standards. It takes an incomprehensible number of atoms just to make a visible speck of dust. A single proton weighs so little that trillions upon trillions of them together barely register on any scale. Particles live in the realm of the almost nothing. That is simply what being a fundamental particle means. Now hold up the Monopole from grand unification. Physicists calculate its mass from the energy at which the force is unified, and that energy is titanic. The result is a particle roughly 10,000 trillion times heavier than a proton. Written out, that means a single monopole could carry the weight of a small living cell, something you would need a microscope to see, packed entirely into one point-like particle. A whole speck of biological life compressed into a single object smaller than an atom. Try to picture the imbalance. A proton is already a busy little thing, and it takes vast numbers of protons to build even a grain of sand. Yet one monopole would outweigh a proton by a factor so large that if you lined up protons to match a single pole, the line would contain more of them than there are stars in millions of galaxies. All of that mass, all of that heft, crammed into one indivisible particle. It is as if nature took the weight of a living organism and hid it inside something far tinier than the smallest atom. Where does all that mass come from? It comes from the knot. Remember that a monopole is a twist in a unified field, and twisting that field into a knot costs energy, enormous energy, because the field is stiff and the twist is tight. Energy and mass are two forms of the same thing, as one famous equation taught the world. So the energy locked inside the knot shows up as mass. The tighter and stiffer the knotted field, the heavier the pole, and the unified field, born at such colossal energies, is stiff almost beyond imagining. Its knots are correspondingly heavy. Think of it like winding a colossal spring. A small spring stores a little energy when you wind it. A gigantic, stiff, industrial spring stores a fortune of energy in a single turn. The monopole is a single turn of the stiffest spring in the universe, the unified field itself, and all that stored energy becomes the pole's staggering weight. This mass reshapes everything about the hunt. A particle that heavy would move with brutal force. If one came drifting through the galaxy, pulled along by magnetic fields in space, it would carry tremendous momentum, ploughing forward like a cannonball rather than fluttering like a leaf. It would be slow to turn, hard to stop, and utterly unlike the flighty featherweight particles physicists usually chase, and the mass creates a brutal practical problem, the one that dooms a certain dream. If you wanted to make a monopole in a laboratory, you would need to concentrate its entire mass worth of energy into a single tiny spot. That is how particle makers build heavy particles, by pouring energy into a collision until a new particle condenses out of it. For a monopole this heavy, the energy required is so far beyond any machine humans could ever build that the whole idea collapses. No collider, now or ever, could come close. If we cannot make one, then every monopole in existence had to be born somewhere else, at some other time. To forge a single monopole, humanity would need a collider larger than anything that could ever fit on Earth. The most powerful particle machine ever built is the Large Hadron Collider, a ring 17 miles around buried beneath the border of France and Switzerland. It whips protons to nearly the speed of light and smashes them together, concentrating energy into tiny points to create heavy particles. It found the famous Higgs particle this way. It is a triumph of engineering, the closest thing we have to a machine that recreates the conditions just after the beginning of time, and it falls hopelessly short of making a monopole. The energy needed to condense a grand unified pole into existence is about 10 trillion times greater than the energy the Large Hadron Collider can reach. No slightly bigger machine could close a gap that size. It is a chasm so wide that no reasonable increase could ever bridge it. Try to imagine building a collider powerful enough. Physicists have estimated the size. To reach the energy of grand unification with current technology, you would need a ring not 17 miles around, but one stretching across distances that dwarf the entire solar system. Some estimates put the required machine at a scale comparable to the space between stars. You would have to wrap a particle accelerator around a chunk of the galaxy. No civilization we can imagine could build such a thing. Here is a way to feel the difference. Suppose the energy the Large Hadron Collider reaches were represented by the height of a single sheet of paper. The energy needed to make a monopole, on that same scale, would tower far higher than any mountain, higher than the atmosphere, reaching a stack of paper you would have to measure against the distance to other planets. The everyday triumphs of particle physics sit at the bottom of that stack, and the monopole waits at a height no ladder could ever climb. This is a humbling wall. For most exotic particles, physicists can dream of a next machine, a bigger ring, a cleverer design that might one day reach them. The monopole from grand unification sits beyond all such dreams. Its energy belongs to a realm we can describe in equations but can never recreate, the realm of the universe's first sliver of a second, when everything was unimaginably hot. So the collider path is closed. Whatever monopoles exist, human machines did not make them, and never will. This might sound like defeat. If we cannot manufacture the thing we seek, how can we ever study it? But the impossibility carries a hidden clue. It points backward in time. There was exactly one place in all of history where the energy of grand unification was freely available, splashed across every corner of space: the early universe. In its first fraction of a second, the whole cosmos blazed at temperatures far beyond what any collider could reach. If monopoles were ever going to be made, that was the moment, the only moment, when nature had the power to make them. The universe itself was the only machine ever hot enough. And it ran that machine once, at the very beginning, for the briefest instant. Which means the monopoles we hunt today, if they exist at all, are unbelievably ancient, forged in the opening breath of creation and drifting ever since. The question becomes how many the young universe stamped out in that fiery moment. In the universe's opening instant, monopoles condensed out of the cooling cosmos like frost forming on a window. Picture the universe, an unimaginably tiny fraction of a second after it began. Everything is packed together, blazing at a temperature so high the forces of nature are still fused into one. Then, as space expands, it cools. And at a certain critical moment, the cooling universe crosses the temperature where the unified force must break apart into the separate forces we know. This is the moment of freezing, the cosmic phase change, and it happens everywhere at once. But here is the crucial detail. The universe was expanding so fast that different regions of space had no way to communicate. Light itself, the fastest messenger there is, had only had time to cross tiny distances since the beginning. So as the great freeze swept through, each little region had to choose how its field would settle down entirely on its own, blind to what its neighbours were doing. One patch settled one way, the patch beside it settled another. Countless tiny regions across the infant universe each made their own independent choice. Where these mismatched patches pressed against each other, their fields could not smoothly agree. At the boundaries and corners where several disagreeing regions met, the field got trapped in a twist it could not escape. Each trapped twist was a monopole. The universe, freezing too fast for its regions to coordinate, litters itself with these knots automatically. Physicists worked out that you would get roughly one monopole for every little region that was out of touch with its neighbours. Think of a huge crowd told to suddenly face the same direction, but with everyone blindfolded and unable to see anyone beyond arm's reach. People near each other might manage to line up, but across the whole crowd, pockets would end up facing different ways, and at the seams between those pockets, the mismatch would be stuck, impossible to fix. The early universe was that blindfolded crowd, and the stuck seams were monopoles. The trouble is that in those first moments, the regions out of touch with each other were absurdly small. Light had crossed almost no distance at all, so the universe was carved into an enormous number of these tiny independent patches, which means it should have produced an enormous number of monopoles. The math is blunt. Small patches mean many seams mean many poles, and remember, these poles are immortal. Once made, they can never decay, so every single one forged in that first flicker of time should still exist today, spread through the universe, heavy and permanent. To count how many should be around us now, physicists simply take the huge number made at the freeze and carry it forward across all of cosmic history. When they did that arithmetic, The result was a disaster. The number of monopoles predicted was so vast that their combined weight would utterly dominate the universe. There would be so much mass locked in poles that the cosmos would look nothing like the one we actually see. The stars, the galaxies, the gentle expansion we observe, all of it would be impossible. The theory that so elegantly demanded monopoles had just predicted far too many of them, enough to wreck reality as we know it. Something was badly wrong, and fixing it would require one of the boldest ideas in the history of science. The universe, it seemed, needed a way to hide almost every monopole it had ever made. By the late 1970s, physics had a beautiful theory that made a catastrophic prediction. Granunification was thrilling. It fused three forces into one. It explained the tidiness of electric charge, and it made bold claims that could be tested. Physicists were excited. But when they carefully counted the monopoles the early universe should have produced, the theory turned on them. The number was ruinous. The calculation said monopoles should be roughly as common as the protons and neutrons that make up ordinary matter. That sounds harmless until you remember the mass. Each monopole weighs about 10,000 trillion times more than a proton. So if poles were nearly as numerous as protons, but each one carried the weight of a small living cell, then the total mass of all the monopoles would swamp everything else in the universe by a colossal factor. Ordinary matter, all the stars and gas and galaxies, would be a rounding error next to the crushing weight of the poles, a universe that heavy could not behave like ours. Gravity responds to mass, and a cosmos overloaded with monopole mass would have felt its own weight far too strongly. Instead of expanding gently for billions of years the way our universe has, it would have slowed, stopped, and collapsed back on itself in a cosmic blink, long before stars or planets or people could ever form. The monopoles would have strangled the universe in its infancy. Sit with the strangeness of this. The same theory that so elegantly demanded monopoles also predicted so many of them that the universe should have destroyed itself almost immediately. A triumph and a disaster wrapped in the same equations. The math that gave physicists the monopole with one hand snatched away the whole universe with the other. This became known as the monopole problem, and it was a genuine crisis. Physicists deeply admired grand unification. Its successes felt too good to abandon. Yet this monstrous overproduction of poles seemed to prove the theory could not be the full story. Either grand unification was wrong, which many were reluctant to accept, or something dramatic had happened in the early universe to erase almost all of the monopoles it made. Think of a factory that runs perfectly, producing flawless goods, except that its own design guarantees it will bury itself under a mountain of a single product until the whole building collapses. The blueprint is elegant, the engineering is sound, and it dooms the factory. That was grand unification and its monopoles. The theory worked too well at making a thing that should have crushed everything. For a while, this hung over physics like a dark cloud. A cherished theory seemed to demand a universe that could not exist. Something had to give. Either the beautiful idea of unification had to be thrown out, or a new piece had to be added to the story of the early universe, a piece powerful enough to take a cosmos drowning in monopoles and sweep them almost entirely away. The answer, when it came, did far more than solve the monopole problem. It rewrote our whole understanding of how the universe began. A young physicist wrestling with exactly this puzzle stumbled onto an idea so sweeping that it explained not only where the monopoles went, but why the universe is smooth, why it is flat, and why it looks the way it does on the larger scales. The idea was that the infant universe, for one unimaginable instant, ballooned in size faster than anyone had ever dared to think. In 1980, a young physicist named Alan Guth was worrying about monopoles when he stumbled onto an idea that reshaped cosmology. Guth was thinking hard about the monopole problem, that ruinous flood of poles the early universe should have made. And in working through the physics of the young cosmos, he realized something astonishing might have happened in its very first moments. The universe, he found, could have gone through a burst of expansion so violent, so explosive, that it defied all ordinary intuition. In a sliver of time almost too small to name, space itself could have stretched, doubling in size again and again and again, until a region smaller than a proton ballooned to something enormous. He called it inflation. The idea is that for one brief, extraordinary instant, the universe expanded at a furious, accelerating pace, growing by an unthinkable factor in almost no time at all. Then, just as suddenly, the wild growth ended, and the universe settled into the calmer expansion we still see today. The whole frantic episode was over in a flash, but in that flash, everything changed. Now watch what inflation does to the monopoles. Suppose the poles were made just before or during this burst of expansion. As space explodes outward, it carries the monopoles apart from each other at a staggering rate. Two poles that started side by side are flung to opposite ends of a suddenly gigantic universe. The dense crowd of monopoles is spread so thin, so violently diluted, that in any patch of space you might look at, there is almost nothing left. The flood becomes a drought. Picture a few grains of pepper sprinkled on the surface of a deflated balloon. Then you blow the balloon up, not to the size of a party balloon, but to the size of a planet. The pepper grains, once close together, are now separated by continents of empty rubber. You could search a huge stretch of the surface and find not a single grain. Inflation did that to the monopoles, blowing up the universe so enormously that the poles were scattered to almost nothing. This was the rescue grand unification desperately needed. Inflation took a universe that should have been drowning in monopoles and stretched it until the poles were diluted down to a mere whisper. The theory could keep its beloved unification, keep its prediction that poles are made, and still match a universe that clearly is not overrun by them. The monopoles were made exactly as predicted. They were simply flung so far apart that they became fantastically rare. And here is the part that turned a patch job into a revolution. Inflation solved far more than the monopole problem. The same violent stretching explained several other deep puzzles that had nothing obviously to do with poles. It explained why the universe looks so smooth and uniform in every direction, why it appears so precisely balanced between expanding forever and collapsing, and where the seeds of galaxies came from. One bold idea, born from worrying about monopoles, tied together a whole cluster of cosmic mysteries. Today, inflation is a cornerstone of how physicists understand the birth of the universe, supported by detailed measurements of the faint afterglow of the beginning. And it all traces back in part to the embarrassing overabundance of a particle no one had ever seen. So the Monopoles shaped our theory of creation itself, even in its absence. But inflation also delivered a stark verdict on the hunt. It told scientists roughly how rare the poles would be, and that number was enough to break a searcher's heart. After inflation did its work, there might be only a single monopole in the entire visible universe, and that is a devastating thing to hear if your job is to find one. Inflation stretched space so violently that it scattered the original monopoles almost beyond existence. When physicists pushed the numbers to their extreme, they found that the dilution could be so severe that the observable universe, all the countless galaxies we can see in every direction, might contain just one leftover pole, or none at all within our reach. Searching for a specific particle when there may be only one in the whole cosmos sounds like searching for a specific grain of sand somewhere across every beach and desert on 1,000 worlds. If that were the end of the story, the hunt would be hopeless, and physicists would have quietly given up. But the picture has cracks of light in it, and those cracks are why the search continues with real hope. The first crack is uncertainty. The exact number of monopoles left after inflation depends on details no one knows for sure, like precisely when the poles were made and precisely how inflation unfolded. Shift those details a little, and the predicted number swings wildly. In some versions, the universe is nearly empty of poles. In others, a modest population survives, thin but real, drifting through the galaxies in numbers large enough to catch if you watch patiently. The honest answer is that scientists do not know how many are out there, and that uncertainty leaves the room for discovery. The second crack is that grand unification is only one recipe for making monopoles. Other theories predict poles that are far lighter, thousands or millions of times less massive than the grand unified giants. Lighter poles could be made more easily and more recently, in processes that inflation would not have swept away. Some might even be light enough to create in powerful collisions here on Earth. A whole family of possible monopoles exists, ranging from the colossal relics of unification down to lighter cousins that ordinary physics might still produce. Think of it like fishing in an ocean where you are not sure what swims below. The rarest, biggest creature might appear only once in a lifetime of casting, if ever. But there may also be smaller relatives of that creature, more numerous, more catchable, swimming closer to the surface. You keep your lines in the water because the ocean is deep and your knowledge of it is incomplete, and any catch would be the discovery of a lifetime. This is the mindset of the monopole hunter. The prize is so enormous, so transformative for physics, that even a slim chance is worth chasing. Finding a single pole of any kind, heavy or light, would confirm that magnetic charge is real, vindicate Dirac's century-old insight, and hand physicists a direct piece of evidence from the deepest layers of nature. The reward justifies decades of patient watching, even against long odds. So scientists refused to surrender. They built detectors and waited. They watched for the violent trail a pole would carve, the sudden signal it would leave, the fingerprint no other particle could fake. Across the world, in deep mines and quiet laboratories, machines sat silent and alert, listening for the passage of a single ancient particle. And on one ordinary Sunday afternoon, in an empty laboratory in California, one of those machines recorded exactly the signal everyone had been dreaming of. There was just one problem. Nobody was in the room to see it happen. To catch a monopole, one physicist built a loop of wire that could feel a single magnetic pole pass through it and remember it forever. The method rests on a beautiful piece of physics. Take a ring made of a special material called a superconductor, cooled until electricity flows through it with zero resistance. In such a ring, once a current starts, it never stops. It circles endlessly, losing nothing, a perfect and permanent memory of whatever set it going. Now think about what happens when a magnet moves through the ring. A changing magnetic field pushes on the electrons in the wire and stirs up a current. This is the same effect that generates electricity in every power plant, a moving magnetic field creating a flow of charge. Here is the clever part, the part that makes the ring a perfect monopole trap. When an ordinary magnet with its two poles passes through the loop, it produces a current in one direction as the North Pole enters and an equal current in the opposite direction as the South Pole follows. The two effects cancel. The ring ends up back where it started, with no lasting current. A normal magnet passes through and leaves no permanent trace, because its two poles undo each other. A lone monopole is different in a way the ring can feel. With only a single pole, there is nothing to cancel. As the pole passes through, it drives a current in one direction, and no opposite pole comes along to undo it. The current starts, and in a superconductor it never stops. The ring is left circling with a permanent steady current that was not there before, a current of a very specific size set by the size of the magnetic charge. That leftover current is the unmistakable signature of a lone pole. A dipole leaves the ring blank. A monopole leaves it forever changed. Picture a turnstile that spins one way when a person walks through and spins back when they walk out, ending at rest. That is an ordinary magnet coming and going, leaving the turnstile as it found it. Now picture a ghost that walks in and never walks out, leaving the turnstile spinning on its own with no way to stop. That impossible, one-way passage is what a monopole would do to the ring. It would leave behind motion that has no ordinary explanation. This design has a wonderful property. It cares only about magnetic charge itself, about the pure fact of a lone pole crossing the loop, ignoring how fast the pole moves, how heavy it is, or which direction it comes from. That makes it one of the cleanest possible tests. A permanent current of the right size means a monopole passed through, and almost nothing else in nature could produce that exact result. The physicist Blas Cabrera built such a ring at Stanford University, shielding it carefully from stray magnetic fields, cooling it to the frigid temperatures superconductors need, and setting it to watch continuously. Then he did the hardest part of all. He waited. Day after day, the ring circled quietly, its current steady, recording nothing unusual. Small blips came and went, far too weak to be a pole. Months passed with no sign of the one clean signal he was hoping for. He could not sit and stare at the apparatus forever, so he let a computer watch it and log any events, checking the record only now and then. Which is how, on Valentine's Day of 1982, the most famous single event in the history of Monopoly hunting happened with no human being anywhere near it. On February 14th, 1982, while the laboratory sat empty, a computer quietly recorded the cleanest Monopoly signal anyone has ever seen. Blas Cabrera had gone home for the weekend. Valentine's Day fell on a Sunday that year, and there was no reason to sit beside a machine that had spent months recording nothing but faint, meaningless blips. His superconducting ring circled on its own in the cold, watched only by the computer logging its every twitch. And at nearly 2 o'clock that afternoon, the current in the ring jumped. The jump was a clean, sharp step of exactly the size a single Monopoly should produce, far larger than the faint partial signals that had come and gone for months. It matched Dirac's prediction with almost eerie precision. Cabrera had designed the ring so that a lone pole carrying the basic magnetic charge would shift the current by a very particular amount, and here was a shift of precisely that amount, recorded in one instant, then holding steady. The ring had been permanently changed, exactly as a passing monopole would change it. When Cabrera returned to the laboratory the next day and looked at the record, he must have felt his heart pound. There in the data sat the signal he had been chasing. The one clean event that could mean magnetic charge was real. A single lone pole appeared to have drifted through his ring on a quiet Sunday afternoon, leaving behind the unmistakable fingerprint the whole design was built to catch. Everything about the event matched the theory. The size was right, the sharpness was right, the permanence was right. Word spread fast and the physics world lit up with excitement. If the event was real, it was one of the most important discoveries of the century, direct evidence for a particle predicted half a century earlier by Dirac and demanded by the grandest theories of nature. A single monopole passing through a ring in California would confirm that the universe really did contain lone magnetic poles, that Maxwell's zero could be erased, that the deep symmetry physicists had dreamed of was real. But science has a strict and unforgiving rule. A single event, no matter how clean, is never enough. To trust a discovery, other scientists must see it again. The result has to repeat. One perfect signal, witnessed by no one and never seen a second time, sits in a lonely and painful place, too beautiful to dismiss and too solitary to believe. Cabrera knew this better than anyone. A lone event could be a true monopole. It could also be some rare mechanical hiccup, a jolt to the apparatus, a fluke in the electronics, a prank, a stray disturbance that happened to mimic the exact signal he sought. The only way to know was to catch another. So Cabrera and others built bigger rings, larger loops with more area, machines far more likely to snare a second pole if poles were truly drifting through. They cooled them, shielded them, and set them watching. The trap was reset, larger and hungrier than before, and the whole community held its breath. Then they waited, and waited. The larger detectors ran and ran, sweeping up far more chances than the original ring ever had. And in all that time, across all those improved machines, not one of them ever caught another monopole. The signal from Valentine's Day stood alone, and as the silence stretched on, it began to look less like a discovery and more like a ghost. A year after the famous signal, a Nobel Prize winner sent Cabrera a Valentine's poem teasing him about the monopole that never came back. The physicist Steven Weinberg, one of the architects of our modern understanding of forces, wrote Cabrera a short rhyme for the next Valentine's Day. Roses are red, violets are blue, it teased, it is time for Monopoly number 2. The joke carried a serious point wrapped in affection. The whole world of physics was waiting for a second pole, and the waiting was becoming an ache. One signal had electrified everyone. A second would have made history. Its absence grew louder with every passing month. As the larger detectors kept running and kept finding nothing, the mood shifted from excitement to doubt. Physicists began to reason it through coldly. If monopoles were common enough to drift through Cabrera's small ring on a random Sunday, then the bigger, later detectors, watching far more space for far longer, should have caught many more. They caught none. The numbers simply refused to fit the idea that the Valentine's event was a real pole among many. a universe with enough monopoles to explain that one clean signal would have lit up the newer machines again and again. So the community reached a reluctant conclusion. The Valentine's Day event, for all its perfect appearance, was almost certainly not a monopole. Something else must have caused it. Some rare disturbance that happened to mimic the exact signal Cabrera was hunting for. A tiny mechanical shift in the apparatus, a jolt from outside, a fluke in the electronics, even a deliberate prank by someone with access to the lab. Any of these could, in principle, have nudged the ring by just the right amount at just the wrong time. No one ever proved which explanation was correct. The cause remains genuinely unknown to this day. And that is what makes the Valentine's Day monopole so haunting. It was never explained, and it was never confirmed. The signal sits in the record exactly as clean as the day it appeared, matching the theory perfectly, and yet standing utterly alone, unrepeated across decades of harder searching. Scientists cannot call it a discovery because science demands repetition. They also cannot fully dismiss it because nothing has ever accounted for it. It floats in a strange limbo, a perfect fingerprint with no proven owner. Picture finding a single flawless footprint in fresh snow, exactly the shape of a creature you have long believed in, and then never finding another print anywhere, no matter how far or how long you search. You cannot claim you found the creature. One print falls short of proof, yet you can never quite forget that perfect shape in the snow or stop wondering what made it. The Valentine's Day event is physics holding on to that one footprint, unable to celebrate it and unwilling to erase it. The lesson stung, but it sharpened the search. It taught monopole hunters that a single event, however beautiful, could never be trusted alone. Any real discovery would have to be caught cleanly, more than once, in machines designed so carefully that no fluke could counterfeit the signal. The bar was raised and the hunt grew more rigorous because of that lonely afternoon in California. The superconducting ring had reached its limit. To push further, scientists would need entirely new ways to trap a pole and new places to look. Some turned their eyes to the sky, reasoning that if ancient monopoles drift through the galaxy itself might reveal them. They found a clue hidden in the magnetic field that threads through the stars. The Milky Way carries a vast, faint magnetic field stretched across its entire spiral, and that field acts as a monopole counter. Our galaxy is threaded through with magnetism. It is thousands of times weaker than a toy magnet, yet it stretches across almost unimaginable distances, spanning the whole disk of stars. This galactic magnetic field has been building and persisting for a very long time, and it plays a role in how gas moves and how cosmic particles travel through the galaxy. It is a delicate, long-lived structure, and delicate, long-lived structures can be used to set limits on things that would disturb them. An astrophysicist named Eugene Parker realized that monopoles, if they were common, would drain this galactic field. Here is why. A magnetic field pushes on a magnetic pole, giving it energy and flinging it along, the same way an electric field pushes a charge. Every time the galactic field accelerates a passing monopole, the pole steals a little energy from the field. If monopoles were plentiful, the galaxy would be full of them, constantly siphoning energy away, and the magnetic field would weaken and fade. It could not have survived to the strength we measure today. But we do measure a healthy galactic magnetic field. It is there, spread across the Milky Way, clearly still going strong, and that simple observation places a firm ceiling on how many monopoles can be drifting through the galaxy. There cannot be too many, because if there were, they would have bled the field dry long ago. The very existence of galactic magnetism, still robust, tells us that monopoles must be rare. This clever argument is called the Parker bound, and it is beautiful because it turns the whole galaxy into a detector. You do not need to catch a single pole to learn something about how many there are. You only need to notice that the galaxy's magnetic field is still standing and reason backward to how few monopoles could allow that. A structure the size of the entire Milky Way becomes a quiet witness, testifying that lone poles, whatever their story, are scattered thin across the stars. Think of the galactic field as a great sail stretched across the galaxy, holding a steady wind. Each monopole that passes is like a tiny hole poked in the sail, letting a little wind escape. A few holes, and the sail still catches the wind fine. Too many holes, and the sail goes slack, the wind gone. We look up and see the sail still full, still holding, which means the holes must be few, the monopoles must be scarce. The Parker bound fit neatly with what inflation had already suggested. Both pointed the same way, toward a universe where monopoles are extremely rare, thinly spread, hard to find. One argument came from the birth of the cosmos, the other from the magnetism of our own galaxy, and they agreed. Poles are out there, perhaps, but few and far between. This rareness is sobering for anyone hoping to catch one, yet it also refines the hunt. It tells scientists roughly how sensitive their detectors must be, how much space they must watch, how patient they must become. To catch something this rare, you cannot rely on a small ring in a single lab. You need enormous detectors, watching huge volumes for long stretches of time, waiting for the vanishingly rare crossing of a single ancient pole. So the search grew in scale, spreading into deep mines and buried tanks and eventually into a cubic mile of ice at the bottom of the world. To catch a rare pole drifting from space, physicists buried enormous detectors under mountains and inside glaciers. If ancient monopoles are streaking through the galaxy, some of them should pass through the Earth, and through any detector large enough to wait for them. The problem is that they are rare, and the crossings are precious, so the detector has to be huge and it has to run for years. It also has to be shielded from the constant rain of ordinary particles that pours down from the sky, which is why so many monopole experiments sit deep underground, under thick rock that blocks the everyday clutter and lets only the rarest, most penetrating visitors through. One major experiment, built inside a mountain in Italy, used layers of detectors spread across a vast underground hall to watch for the telltale signature of a pole. A monopole crossing those layers would leave a trail unlike any common particle, moving in a characteristic way and depositing energy along a long straight path. The experiment ran for years, patiently sweeping through its enormous volume, watching for the one crossing that would change physics. It found none, and its silence was valuable. By seeing no poles despite watching so much space for so long, it tightened the limits on how many monopoles could possibly be drifting through and how fast they could be moving. Then physicists went further and turned a piece of Antarctica itself into a detector. Deep in the ice at the South Pole, they sank strings of sensitive light detectors more than a mile down into the clear ancient glacier, instrumenting a full cubic mile of ice. This giant, called Ice Cube, was built mainly to catch ghostly particles called neutrinos, but it doubles as a monopole trap. A pole tearing through the ice would trigger a distinctive burst or streak of light as it disturbed the material around it, and the buried sensors would catch that glow, mapping the intruder's path through the frozen dark. Picture a cubic mile of perfectly clear ice, threaded with thousands of unblinking electronic eyes, sitting in absolute silence beneath the polar surface. For years, those eyes have stared into the ice, waiting. If a monopole ever plunges through, the ice would light up along its track and the eyes would record it. So far, the ice has stayed dark of poles. But the watching continues, because the volume is so vast that even an incredibly rare crossing has a chance of being caught. Other searchers looked in stranger places still. Some scanned old rocks and ancient minerals, reasoning that if a monopole passed through them long ago, it might have left a permanent scar frozen in the crystal, a fossil trail waiting to be found. Some searched moon dust and meteorites, samples that had been exposed to space for eons, in case a pole had lodged inside. The hunt spread across the Earth and beyond into ice and stone and starlit samples. Everywhere a patient pole might have left its mark. All of these searches share one frustrating result and one quiet triumph. The frustrating result is that none of them has ever caught a monopole. The quiet triumph is that each failure carves away another slice of possibility, telling us with growing confidence that poles, if they exist, are rarer and stranger than we might have hoped. Yet all these experiments waited for poles that nature had already made and sent drifting toward us. A bolder idea was taking shape. Rather than waiting for an ancient pole to arrive, why not try to create a fresh one, right here, in the most powerful machine on Earth? At the world's largest particle collider, a quiet and mostly motionless experiment waits for a monopole to leave its mark. The Grand Unified Monopole is far too heavy for any machine to make, as we saw. But lighter monopoles, predicted by other theories, might be within reach of the Large Hadron Collider, which concentrates more energy into single collisions than anything else humans have built. If a lighter pole exists at an energy the collider can reach, then when protons smash together at nearly the speed of light, a pair of poles, one north and one south, might occasionally burst into being. To catch such an event, physicists built a special detector called Moedl, whose name points to its purpose of hunting monopoles and other exotic particles. Moedl is unusual among collider experiments. Most detectors are dazzling towers of electronics, crammed with sensors that read out millions of signals every second. Moedl is mostly passive and silent. It is built largely from sheets of special plastic and from blocks designed to trap and hold any monopole that wanders in. It sits near one of the points where the collider's beams cross and particles are born, and it simply waits, absorbing whatever the collisions throw at it, recording their passage in permanent damage rather than electronic flashes. The plastic sheets work on the principle we met earlier. A monopole, with its fierce magnetic charge, would tear through the plastic far more violently than any ordinary particle, leaving a line of intense damage along its path. Later, scientists soak the sheets in chemicals that widen these damage tracks into tiny cone-shaped pits, then examine them under microscopes. A monopole would betray itself as a line of unusually large pits marching through the plastic, a scar no common particle could carve. The detector catches this without power or fast electronics. It only needs to sit in the right place and be read out carefully afterward. The trapping blocks are even more direct. A monopole, once created, could get caught and held inside dense material, snagged by its magnetic charge. Moedl includes large volumes of such material, positioned to catch any poles born in the collisions. After a period of running, scientists remove these blocks and pass them through an extremely sensitive version of the superconducting ring, the same kind of device Cabrera used. If a trapped monopole rides through the ring inside the block, it would leave that permanent telltale current, revealing that a pole had been captured. Picture a fisherman who lowers a net into the exact spot where the current runs strongest, then leaves it there for months, trusting that if the rare fish exists, it will eventually swim into the waiting mesh. Moedl is that patient net, hung in the fiercest current of particle physics, waiting for a monopole to swim in and be held. For years now, Moedl has watched the collisions, gathered its plastic and its blocks, and searched them with painstaking care. And its result so far echoes every other monopole hunt in history. It has found no poles. But like the others, its silence still teaches. Each search sets the strongest limits yet on how heavy a monopole could be, while still escaping detection, ruling out more and more of the places a pole could hide. And the physicists behind it wanted more than to wait passively for poles to appear from ordinary collisions. They began to wonder whether they could force poles into existence using one of the strangest tricks in all of physics, by tearing them straight out of empty space. There is a way to pull particles straight out of empty space if you can create a field strong enough, and physicists tried it on monopoles. Empty space is a busy place at the smallest scale. The vacuum churns with fleeting activity, pairs of particles and their opposites flickering into being and vanishing again, borrowing energy for the briefest instant before paying it back. Usually these pairs appear and disappear too fast to matter. But if you apply a strong enough field across that churning vacuum, you can grab such a pair before it vanishes and yank the two partners apart, turning them into real, lasting particles. You would be pulling matter out of nothing but a field. This idea is named after the physicist Julian Schwinger, who worked out how it happens for electric charges in a powerful electric field. The same trick should work for monopoles in a powerful magnetic field. If you could create a magnetic field of staggering strength, it could reach into the vacuum, grab a flickering pair of poles, one north and one south, and rip them apart into real permanent monopoles. The stronger the magnetic field, the more likely this becomes, so the question turns practical. Where in the universe, or in any laboratory, can you find a magnetic field fierce enough to tear poles from the void? The answer is astonishing. When two heavy atomic nuclei, stripped bare and hurled at nearly the speed of light, graze past each other in a collider, they generate for a fleeting moment the strongest magnetic fields ever produced on Earth. These fields tower over the gentle pull of ordinary magnets. As the massively charged nuclei rush by one another, the magnetic field that flares up between them is more intense than anything else humans have ever made, briefly rivaling the fields found around the most extreme objects in the cosmos. For an instant, in the space between two passing nuclei, conditions arise that might just be violent enough to tear a monopole pair from the vacuum. This gave physicists a thrilling new way to hunt. Instead of relying on ordinary collisions to occasionally cough up a pole, they could smash heavy nuclei together and let the ferocious magnetic fields do the work, coaxing poles out of empty space through the Schwinger trick. And this method has a special advantage. For monopoles that are made of smaller pieces rather than being simple point particles, the usual ways of making them in collisions become hopelessly unlikely. Yet the Schwinger method escapes that penalty. If poles are composite objects, tearing them from the vacuum with a monstrous magnetic field might be the only realistic way they could ever be produced and seen. Picture the vacuum as a taut sheet of fabric, and a monopole pair as two beads sewn invisibly into it, normally hidden. A strong enough magnetic field grabs the fabric and pulls, stretching it until the two hidden beads pop free and become real, rolling out into the world. The colossal field between two passing nuclei is that pull, straining the vacuum hard enough for one instant to shake loose a pair of poles. Physicists ran exactly this search, colliding heavy nuclei and then hunting for any poles the extreme fields might have birthed. They scanned their detectors and their trapping material for the fingerprint of a monopole torn from the void. Once again, they found none, and once again they set new limits, closing off another hiding place for the elusive pole, and in their hunt for trapped poles they turned to an unexpected place to search, a discarded piece of the collider that had once stood at the very heart of the collisions. When part of a giant detector was taken out of the collider and set aside, physicists realized it might be hiding monopoles inside it. At the heart of a collider experiment runs a pipe, the narrow tube through which the particle beams travel, and inside which they smash together. That beam pipe sits at the exact center of the action, wrapped right around the point where countless collisions happen. If any monopoles were ever created in those collisions, some of them could have flown outward a short distance and buried themselves in the material of the pipe itself, trapped there by their magnetic charge, held in place ever since. The pipe would be a silent archive of everything that had crashed through its center. So when a section of beam pipe from one of the major experiments was eventually removed and decommissioned, physicists saw an opportunity. That old pipe had spent years at the center of a storm of collisions. If poles had been made and caught in it, they would still be there, locked in the metal, waiting. All you had to do was take the retired pipe and check it carefully for the presence of any trapped magnetic charge. The check used the familiar tool, the superconducting ring. Scientists passed pieces of the old beam pipe slowly through an extremely sensitive version of the loop, the same kind of device that had watched for poles since Cabrera's day. If a monopole was hiding inside the metal, then as that piece rode through the ring, it would leave behind the permanent, unmistakable current that only a lone pole can produce. By scanning the whole pipe piece by piece, physicists could search every part of it for a captured monopole, reading the archive the collisions had written. There is something wonderfully resourceful about this. Rather than building a brand new detector and waiting years for fresh collisions, physicists took a discarded piece of hardware that had already been sitting in the perfect spot, soaking up collisions for years, and turned it into a monopole trap after the fact. The pipe had been an unwitting detector all along, quietly collecting any poles that came its way. All that remained was to develop the film, so to speak, and see what had been caught. Picture an old net that spent years hanging in a rushing river, then was pulled out and left in a shed, forgotten. Long afterward, someone realizes that whatever swam into that net during all those years might still be tangled in it, and they carefully comb through every knot to see what the river left behind. The retired beam pipe was that forgotten net, and the superconducting ring was the careful comb, searching the mesh for a single trapped pole. This search offered a special reach. Because the pipe sat so close to the collisions, it could catch poles that flew out at angles or with properties that a normal detector might miss. It complemented the other hunts, covering ground they could not, ruling out possibilities they left open, and like every monopole search before it, it delivered the same answer. No trapped poles were found. The archive, when finally read, held no lone magnetic charge. Another hiding place searched, another limit set, another quiet no added to the long tally. Yet even as the direct searches kept coming up empty, a darker theoretical possibility lurked in the background, one that turned the monopole from a prize into a potential menace. Some physicists calculated that a single pole, if it ever met ordinary matter, might do something terrifying to the protons inside it. A single monopole, drifting quietly through a block of ordinary matter, might cause the protons inside it to fall apart. This unsettling possibility came from studying what happens when a grand unified monopole meets a proton. Recall that these poles are born from the theory that unifies the forces, the same theory that predicts in certain forms that protons themselves can very slowly decay. On their own, protons appear to last essentially forever. The rare decay these theories allow is so slow that a proton would typically survive vastly longer than the current age of the universe. Matter feels permanent because on any human timescale, it is. But two physicists working out the details found something disturbing. When a proton wanders too close to a grand unified monopole, the pole can act like a catalyst, dramatically speeding up the proton's decay. A catalyst is something that makes a reaction happen far faster while remaining unchanged itself. In the presence of the pole, a proton that might otherwise have survived for an eternity could break apart almost immediately, dissolving into lighter particles and a flash of energy. And crucially, the monopole comes through the process untouched, ready to do the same thing to the next proton it meets. This idea carries the names of the physicists who uncovered it, and it describes a pole that could catalyze the decay of matter over and over without ever wearing out. Sit with how strange and frightening that is. A single monopole, moving slowly through a chunk of matter, could leave behind a trail of destroyed protons, each one triggered to decay as the pole passed near. One immortal particle, patiently unravelling the matter around it, converting solid substance into radiation, proton by proton, endlessly. The pole would be a tiny, tireless engine of destruction, and nothing it touched would use it up. Picture a single spark that moves through a field of dry grass, lighting each blade in turn and then moving on, still burning, still hungry, leaving a widening path of ruin while remaining exactly as bright as when it started. A proton-decaying monopole would be that undying spark, drifting through matter and quietly dismantling it, one particle at a time. This grim possibility, oddly enough, gave physicists a new way to hunt. If monopoles catalyze proton decay, then a large detector filled with matter and watched closely might catch the signature of a pole passing through, revealed by a string of proton decays lighting up along its path. Instead of waiting for the faint current of a pole in a ring, scientists could watch enormous tanks of material for the distinctive flashes that a catalyzing monopole would trigger as it dismantled proton after proton. The very danger of the pole became a beacon that might expose it. Detectors built to watch for proton decay, huge underground tanks monitored by thousands of sensitive eyes, joined the monopole hunt on these grounds. They watched their vast volumes for the telltale cascade a pole would leave. And once more, they saw no such thing, adding yet another limit, another closed door to the growing record of searches that found nothing. Still, the proton decay idea deepened the mystery in a productive way. It suggested that a monopole would be one of the most consequential objects in all of nature, capable of destabilizing matter itself. And it fed into an even larger question that had been quietly growing in the minds of physicists and astronomers alike. Could these heavy, immortal, matter-dissolving poles be the hidden stuff that makes up most of the mass of the universe? Most of the matter in the universe is invisible, and for a while magnetic monopoles were a leading suspect for what it might be. When astronomers measure how galaxies spin and how they cluster together, they find far more gravity at work than the visible stars and gas can explain. Something unseen is pulling on everything, something that gives off no light but has plenty of mass. Scientists call this mysterious substance dark matter, and it appears to outweigh all the ordinary matter in the universe by a wide margin. Whatever it is, it dominates the mass of the cosmos, shaping how galaxies form and hold together, and no one has ever directly identified it. Monopoles fit some of the requirements beautifully. They would be heavy, exactly the kind of massive object that could supply a lot of hidden mass. They would be stable, immortal relics that never decay, so any made in the early universe would still be around contributing their weight today. And they would be hard to see in ordinary ways, since a lone pole gives off no light of its own and interacts with normal matter only through its unusual magnetism. Heavy, permanent, and hidden, Monopoles check several of the boxes that dark matter needs to fill. For a time, this made poles an appealing candidate. If the early universe made a modest population of monopoles, thinned by inflation to a survivable number but still substantial, their combined mass might account for the invisible weight tugging on the galaxies. The very particle that Dirac had dreamed up, and that grand unification demanded, might also be the hidden scaffolding of the cosmos. It was an elegant possibility, one strange mystery potentially solving another, but the same arguments that make monopoles rare work against them here. The Parker bound, which showed that too many poles would drain the galaxy's magnetic field, sharply limits how many monopoles can be drifting through space, and that limit turns out to be far too tight for poles to supply all the dark matter. If there were enough monopoles to account for the missing mass, they would have bled the galactic magnetic field dry long ago, and we would still see a healthy field today only by accident. The galaxy's own magnetism testifies that poles are simply too scarce to be the bulk of dark matter. Picture trying to fill an enormous reservoir using a substance you're only allowed to add in tiny amounts, because adding too much would poison the water. No matter how you try, you can never add enough to fill the reservoir without breaking the rule. Monopoles are like that. The galaxy's magnetic field caps how many can exist, and that cap keeps them from ever adding up to the vast weight of dark matter. They might contribute a sliver, but the great bulk of the missing mass has to be something else. So monopoles fell out of favour as the main answer to dark matter, though they have never been entirely ruled out as a minor ingredient. The search for what dark matter truly is continues along other paths, hunting different kinds of unseen particles. Yet the episode left a mark. It showed how a single hypothetical particle could reach into cosmology, particle physics, and astronomy all at once, tying together the smallest scales and the largest. By now, the monopole had touched nearly everything. The tidiness of charge, the unity of forces, the birth of the universe, the stability of matter, the nature of the dark. Yet through all of it, no one had ever held one, or made one, or proven one exists. Then came a discovery that let scientists study monopoles in the laboratory at last, using a clever imitation grown inside a crystal. In 2009, scientists announced they had made objects that behave like magnetic monopoles inside a strange crystal, and the news electrified physics. The crystal belongs to a family of materials nicknamed spin ice, because the way its magnetic atoms arrange themselves follows a pattern echoing the way hydrogen atoms sit inside ordinary frozen water. Inside spin ice, each atom acts like a tiny magnet, a little arrow with a north and a south, and these arrows are forced to point according to strict local rules, much like puzzle pieces that can only fit together certain ways. Cooled to extreme cold, the arrows settle into a frustrated, restless arrangement full of hidden tension. Now comes the beautiful part. When you disturb this arrangement just so, the tiny magnetic arrows rearrange in a way that creates, at certain points in the crystal, a spot that behaves exactly like a lone North Pole, and elsewhere a spot that behaves like a lone South Pole. These spots can even move through the crystal independently, drifting apart, each carrying what looks for all the world like a single, isolated magnetic charge. Inside the material, it is as if monopoles have come to life, wandering through the crystal as separate North and South poles. It is crucial to be honest about what these are. These are emergent imitations, patterns in the collective behaviour of many ordinary atoms that mimic the properties of a real monopole, rather than the fundamental lone poles Dirac imagined. The individual atoms still have both poles, as always, but their combined arrangement produces regions that act like isolated poles, the way a crowd of people can form a wave that travels around a stadium even though no single person moves very far. The wave is real and behaves like a thing in its own right, yet it is made of ordinary people doing ordinary things. Still, these crystal monopoles are far more than a curiosity. They give physicists something they have never had for real monopoles, a laboratory specimen they can create on demand, poke, move, and measure. Scientists can study how these imitation poles behave, how they move through the material, how they respond to fields, testing ideas about monopoles that were purely theoretical for decades. The crystal becomes a playground where the strange logic of lone poles plays out in a form you can actually experiment on. Picture a flight simulator for a spacecraft that has never been built. You cannot fly the real ship because it does not exist yet, but the simulator lets you practice, learn its handling, and understand how it would behave. Spin ice is a kind of simulator for magnetic monopoles, letting physicists rehearse the physics of lone poles using a stand-in they can hold in a laboratory, while the true fundamental pole remains out of reach. These emergent monopoles have become a rich field of study in their own right, teaching scientists about the surprising ways that simple parts can combine to produce behaviour no single part possesses. They blur the line between the fundamental and the emergent, and they keep the dream of monopoles vividly alive even in the continued absence of the real thing. But a simulation, however clever, is still a stand-in. The genuine fundamental monopole has never been caught, and if one ever were, it would refuse to stay a lonely curiosity. A real pole would reach out and bind with ordinary matter, forming objects unlike anything in the current catalogue of nature. A real magnetic monopole would rarely stay purely magnetic. It would tend to pick up electric charge and become something new. Physicists realised early that a lone pole and an electric charge have a natural affinity for one another under the right circumstances. A monopole can capture an electric charge, or be born already carrying one, becoming a hybrid object that has both a magnetic charge and an electric charge at the same time. This two-in-one particle earned its own name. Physicists call it a dion, a single object that is part magnet and part electric charge, fused together. The great physicist Julian Schwinger explored these hybrids in detail, mapping out how a particle could carry both kinds of charge at once. Dions behave in wonderfully strange ways. Because they carry both electric and magnetic charge, they respond to both electric and magnetic fields, and the two charges are locked together by the same tidiness rule that governs poles. A whole zoo of possible dions emerges from the mathematics, each with its own particular blend of the two charges, all following the strict quantized pattern. If monopoles exist, dions almost certainly come along with them, expanding the family of possible particles far beyond a simple lone pole. Then the possibilities grow richer still. A heavy monopole, with its powerful magnetic pull, could grab onto an ordinary atomic nucleus and hold it, forming a bound pair, a strange little partnership between a pole and a piece of everyday matter. Physicists have studied these monopole nucleus systems and found they could form exotic bound states, with properties unlike any ordinary atom. In principle, a monopole drifting through matter could gather a companion, dragging a captured nucleus along with it, wearing a piece of the material it passes through. Picture a lone traveller with a strange magnetic cloak walking through a crowd. As it moves, it picks up objects that stick to the cloak, a coin here, a key there, until it wanders on wearing a patchwork of things it has gathered along the way. A monopole in matter could be like that traveller, collecting electric charge and even whole nuclei, dressing itself in borrowed pieces of the ordinary world, becoming a composite object stranger than either part alone. These ideas hint at a whole hidden branch of possible physics, a kind of matter that could exist only if lone poles are real. There could be exotic atoms built around monopoles instead of ordinary nuclei, new families of dions carrying mixed charges, bound states and structures found nowhere in the current catalogue of nature. A single confirmed pole would do far more than add one particle to the list. It would open the door to an entire unexplored territory of matter, waiting to be mapped. This is part of why physicists find monopoles so tantalizing. The pole itself would be a triumph, but the pole is also a doorway. Behind it lies a landscape of dions and monopole atoms and strange bound states, a whole realm of possible matter that ordinary physics has never touched. To find one lone pole would be to catch a first glimpse of that hidden country. And yet all of this, the dions, the exotic atoms, the vast new territory, rests on a single unproven foundation. Everything depends on whether even one true monopole exists anywhere in the universe, which brings us at last back to the question that started this whole journey. If a single lone pole were finally, undeniably caught, what would it mean for the forces that shape reality? If a single magnetic monopole were caught tomorrow, cleanly and beyond doubt, it would rewrite the foundations of physics in a single stroke. Start with the equations of electricity and magnetism. For over a century they have carried that lonely zero, the flat declaration that magnetic charge does not exist. A confirmed pole would erase that zero forever. The equations would snap into perfect symmetry, electricity and magnetism becoming true and complete mirror twins at last. The wound in Maxwell's beautiful machine would heal. Every generator, every radio wave, every beam of light would still work exactly as before, but the laws behind them would finally stand whole, balanced, symmetric in a way physicists have ached for since the beginning. Then there is the tidiness of charge. We know electric charge comes in exact identical packets, and we have never known why. A confirmed monopole would answer that century-old riddle in an instant. Dirac showed that a single pole anywhere forces all charge to be quantized, so finding one pole would explain at last why every electron in your body carries precisely the same charge, why protons and electrons balance so perfectly, why atoms can be neutral and matter can hold together. One discovery would turn a deep coincidence into an ironclad law. Reach further to the unity of forces. The grandest theories predict that the forces of nature were once a single force, and that monopoles are the scars left when that unity broke. A confirmed pole would be direct, physical evidence that grand unification is real, that the strong, weak and electromagnetic forces truly were one in the searing heat of the young universe. Holding a monopole would be like holding a fragment of that lost unity, a relic from the instant the forces divided, and a pole would be a messenger from the very birth of the cosmos. These particles, if they exist, were forged in the first sliver of a second after the beginning, at energies no machine could ever recreate. Every monopole is an ancient survivor, an immortal witness to conditions we can otherwise only describe in equations. To catch one would be to hold a piece of the newborn universe in your hand, unchanged across nearly 14 billion years, carrying in its very existence the memory of creation. This is why physicists have chased this single particle for nearly a century, through superconducting rings and mountain caverns, through cubic miles of polar ice and the retired pipes of great colliders, through the churning vacuum and the frozen crystals of the laboratory. They have found nothing, over and over, and set limit after limit, closing hiding place after hiding place. And still they search, because the reward is almost beyond measure. A single lone pole would confirm a symmetry, solve a mystery, prove a unity, and deliver a relic of the beginning all at once. The magnet on your refrigerator has two poles, welded together, impossible to separate, as every magnet you have ever touched has been. That simple, stubborn fact has held true in every experiment ever run, and yet the equations whisper that it need not be the whole story, that somewhere out in the vast dark, or buried in the debris of a collision, or drifting through a mile of ancient ice, a single lone pole might be waiting, carrying in its lonely magnetism the power to rewrite every force we know. We have not found it yet, but the search goes on, patient and relentless, because the universe left us a clue in the perfect tidiness of charge, a footprint in the snow hinting that somewhere the walker is real. And the day someone finally catches it, physics will never be the same.